Okay. So today what I want to do is, so we've spent one lecture on network flows, and this is basically covering chapter 5 of your textbook. We're now going to look at chapter 6 of your textbook, which discusses algorithms for solving network flow problems. Chapter 6, if you look at your textbook, is structured into a few sections. It starts with transportation, then it looks at shortest path and maximum flows, and then the minimum cost flow problem. This is a most general problem. So we are going to skip the transportation part because some of that will be sort of implicit in our treatment of min cost flows. So we'll pick things up from the shortest paths and the maximum flows, then do min cost flows, and then do the transportation very, very quickly. Okay. Just waiting for them to. Okay, so let's look at the following. A lot of what we do today is going to be with respect to this particular network. Okay. And the first question is, suppose we are solving the shortest path problem on this network. We want to somehow do this efficiently. So as we said, we could always do this as a linear program. But we want to design algorithms that are specialized and that are much more efficient than solving a general LP. Okay. So let's say that you have this network and you want to find shortest paths from node 1, which is the source, to every other node. Okay. I haven't given you distances so far, but suppose all the distances were 1. Okay. So every arc has unit distance. How would you solve the shortest path problem in that case? Okay. Any suggestions? Yes?
You start from node 1 and then progressively add the closest node to that one. Once you get all the set of connected nodes and the set of unconnected nodes, and each time you keep adding the closest node.
Okay, very good. So basically what you said was the algorithm that we'll discuss in the first half of the class, which is that you start at this node and you just explore this graph. Okay? Now, when you have unit distances, so certainly it is, so let me write out this. So let's say that this is the source, I said. So this has distance 0. Okay? So the shortest path from the source to itself is of length 0. And you mark this as being labeled. Okay, so any node in which there's a red number on top is sort of labeled. Okay, then you can sort of explore those nodes that are in the immediate neighborhood of node 1. So those nodes that you can reach from node 1 in a single step. Okay. Now, because all the arc lengths are unit, every arc has length 1, certainly there is no shorter way to get to node 3 or to node 2, right? So you would label those as 1. Okay. Now again, we can now say that node 1 has been explored, so I can say this is done. Now I'm going to explore nodes from nodes that are marked but not yet completely explored. Okay. So in this example, I have 2 of those nodes, nodes 2 and 3. These are both marked, okay, so they are sort of labeled, but they have not been explored yet. Okay. So what does it mean for a node to be labeled? It just means that you found the shortest path from the source to that node. Okay. And what does it mean for a node to have been explored? You've sort of used the fact that you know the shortest path from the source to that node, and then used to explore all the nodes in its immediate neighborhood. Okay. So you keep doing this until every node is labeled. So this is the idea. This is called breadth first search. Okay. So in the next step, for instance, we can look at node 2 and node 3, and then look at all the nodes that are within unit distance of that node. Okay. So for instance, from node 3, I can reach from node 2, I can reach node 3 in a single step. Okay. But 3 already has a label, so it's not going to give me anything. From 2, I can reach 4 in a single step. So this is going to be marked as 2. From 3 also, I could reach 4 in a single step. From 3, I could reach 5 in a single step, so that's also marked as 2. And if you notice, all the nodes 2 and 3 have both been explored. Okay. So you can now say that they are done, and then you proceed. Okay. So in this little example, you are going to get 3 as the label there, and the red numbers indicate the shortest path distances from the source to each of those nodes. Okay. So again, the idea is that you start at the node and explore the graph in a breadth first manner. First, look at all the neighbors of 1. Okay. Then look at all the neighbors of the immediate neighbors of 1. And anything that you have not encountered yet, you mark them as 2. Okay. Then explore all of the nodes labeled as 2, look at their immediate neighborhoods, and any node that you encounter that has already not been marked, you label as 3, and you continue. Okay. Is this algorithm clear? And why does it work? Why is it correct? Or how would you prove or verify for yourself that this is correct? Yes?
So the distance to node is 1, so you're sure that there is no, when you do that, you're sure that there is not another path that is shorter.
Very good. So basically, there's some kind of an inductive argument, right? That basically what you show is whenever a node gets labeled, it's labeled with the shortest path distance. Okay? And because you're exploring this graph in a breadth first manner, you're going to, if the shortest path is actually k, you're going to see this exactly in the kth step. Okay? You do this exploration. So somehow, this seems like a fairly natural, easy algorithm that works. Yes.
So if you assign like different weights to the path, you would still get the same result by the same algorithm, right?
Yes. So as I said, so we are looking at the special case when all the arc lengths are 1. Okay? Now in that case, this algorithm would work because the shortest path distance is the same. The shortest path length is the same as the number of edges that you traverse to get to a particular node. Okay? So what does it mean for the shortest path from 1 to 6 to be of length 3? Well, there is a path of length 3 from node 1 to node 6, or there is a path with 3 edges from node 1 to node 6, and it's not possible to reach node 6 from node 1 using at most 2 edges. Okay? These are the 2 statements that you need to verify in this model to show that the shortest path length from 1 to 6 is actually 3. Okay?
But I mean, in reality, if you like go 3 paths, that might be like a value of like a weight of like 100, and then if you travel like the 4 paths, actually it's like 70 something.
As I said, right now, all the distances are assumed to be 1. Every arc has distance 1. In that special case, this algorithm gives you the shortest path. We are not looking at arbitrary distances. So in this particular graph, every edge has distance 1.
But I'm still thinking like if for an arbitrary graph, this algorithm still works.
and we are not yet discussing the general case. Okay, so for the special case, let's convince ourselves that this idea works. Okay. For this special case, notice that the shortest path length from node 1 to some node I is k if and only if two statements are true. That node I is not reachable from node 1 using at most k minus 1 arcs. And there is a path using k arcs that reaches node I from node 1. Okay? And both of these statements can be proved just by looking at the structure of the algorithm, right? Because you're exploring things breadth first. If the shortest path distance is k, you would encounter this node I in the kth step and no sooner. The fact that you encounter it in the kth step means that there is a path of using at most k edges, using exactly k edges. So, yes?
What was it that prevented us from exploring 1, 2, 3, 5, 6, that path, which is 4?
1, 2, 3, 5, 6.
Yeah.
Very good. So let's actually understand this. So let's look at this path. 1 to 2, 2 to 3, 3 to 5,
yeah,
and 5 to 6, right? This path has length 4. Why did we not explore this? We did explore this, except that we realized that it was suboptimal implicitly. Okay, so why? Well, we saw that 2 was labeled because of 1. Okay, so whenever we label a node, we can also keep track of who was responsible for labeling that node. Okay, so for instance, I could say node 2 got a label of 1 because node 1 had a label of 0. Okay, so I could just mark this arc in red. Okay, this is the guy that labeled me, and node 3 would do the same thing. Okay. Now, remember that after this step, node 1 has been explored, so we don't do anything with it. But then we explore simultaneously all the neighbors of nodes 2 and 3. Okay? And then label all of their neighbors who are not yet labeled. So in this case, starting from node 2, if you look at its immediate neighborhood, you encounter node 3, because you can go from 2 to 3 in a single step. But 3 is already labeled, so you wouldn't do that. Then you would encounter node 4, okay, which notice you can label because of 3 or because of 2. It doesn't matter. No, we could just say that we are going to label this. So 4 gets labeled this way, and then this gets labeled this way. And then basically the immediate neighbors of 2 and 3 are explored. Then you're going to use 4 and 5 to explore its immediate neighborhood. So you can, let's say we pick one of these. Okay? So every node now not only has a label, but also has a pointer to who labeled it. Okay? And this way you can recover a shortest path. And now you see why that green path would not be explored. Okay. Yes?
Essentially, this network, you don't backtrack and you don't relabel the node again, right?
That's correct. So in this particular way of solving the problem, we don't do any relabeling. There are other methods that would do relabeling that we'll discuss. But this one is what's called a label setting algorithm. It just computes the label directly. Okay. By label, we mean shortest path lengths. Okay. So the path, the green path, node 3 has a distance of 2, and you would not use that at all. Okay. So 1 to 3, because there's a shorter path, you would use that instead. Okay, so I think it's sort of fairly easy to verify that this algorithm is correct if you have unit length arcs. Okay. Now what happens if you have arcs of arbitrary length? So let me draw the same network. I should have actually just copied it, but anyway. It may be easier to do this on the board because I want to say a few things that's important. So let's actually look at the same network. Okay. So here is node 1. Here's 3. Here's 2. Here's 5. Here's 4. And here is 6. Okay. Now suppose the distances are 4, 6, 2, 2, 1, 2, 2, 2, 1, and 2. Okay. So this now gets to the case that you are interested in, which is that you have arbitrary length arcs. So the natural question is there any way for us to reduce this to the problem that we know how to solve? Okay. We could do the following, right? I could take this and remember that this has length 4. I can do the following. I could say okay. So all the green nodes are nodes that are not nodes of the original problem, but we're using so that we can implement the algorithm that we know works. Okay. And of course, if I take this, I would say, sorry, that was length 2. Right? So anything that already has a length of 1, you don't have to replace. But any other arc length, you can replace by the necessary number of intermediate nodes. So if its length is 4, you need to use 3 intermediate nodes and so on. So if its length is k, you would use k minus 1 intermediate nodes. And then you do the same thing. Okay. Would that work? Is everyone comfortable with the idea that you take a length of an arc of arbitrary length and replace it by a bunch of unit length arcs, such that collectively it does what you want it to? The claim is that any shortest path length, any shortest path in this problem gives you a shortest path in the problem you started with, and vice versa. Okay. That's obviously true. Of course, in this problem, you only care about paths from node 1 to all the red nodes, and you don't care about the green nodes, because the green nodes are auxiliary nodes that you introduce to solve the problem. Okay? So certainly it does work, and you should convince yourself that it does work. Okay? What are the difficulties? So obviously the advantage is that if you have arcs of unit length, we know how to solve the problem. It's a very simple algorithm. And so for general networks, I can do the same thing. What are the disadvantages of such a method? Yes?
You increase the number of nodes.
You increase the number of nodes. If I have, it's very easy for me to put this length to be 1,000,000, and then you're going to now put 1,000,000 minus 1 intermediate nodes, right? I mean, so somehow the size of the network that you're looking at increases with the numbers. That's not very good. Okay? There could be other problems. Yes? If you have non-integer distances, it's a problem, right? But one can sort of deal with it in the following way. If you have rational distances, then you can make them all integers. But then if you have irrational distances, then even that trick wouldn't work. Okay? So suddenly it doesn't seem like a natural thing to do, right? If you have fractional distances, then you get into some difficulty. Yes?
I didn't get that. Why the weight is not integers that will be a problem?
If this distance is 3.5, I only know how to deal with unit length edges. So how can I get a distance of 3.5? So this way I simulate a distance of 4, right?
But you can always assign the weight at 2 that should be like 3.5, right?
No, there is no weight, right? We want all the distances to be unit length. Okay. There's no notion of weight there are no weights associated with nodes. So in this problem you have a network and you have distances.
Yeah, but if I just come up with an algorithm like from 1 and to 2, and it's the path weight is like 3.5, I just say and mark like 2 to be like 3.5. If any other path comes to 2 and leads to 2 is like less than 3.5, I mark 2 to the lower value.
That's certainly valid, and we are going to get to something like that in a moment. But right now, I just want to show you that we know how to solve the problem where all the arc lengths are 1. And then any general problem, we want to reduce to that case, and we want to see what happens. Now, one of the difficulties is you blow up the size of the network. The other difficulty is that this reduction is not clear how to do if you have non-integer arc lengths. Okay? Even worse, there are applications where you could have negative distances. Okay? I mean, when it's not a distance, when it's something else, then it's even less clear what you would do. Okay? So, this is nice, but it's an overkill. Okay? But let's actually understand how this would work. Okay? So, what would happen if I actually do this replacement? Okay? You would still start at node 1, and then what would you do in the next step? You're going to label, so this is going to have a label of 0. Okay. I'll find a blank. Okay, I'm afraid I have to use red for the labels as well. So this has a label of 0. Then what nodes will you label next? Label these two things as 1, right? And then you would label this as 2. Then you would label this as 3. Then you would label this as 4. Okay. And that's when something interesting happens, right? That some node you care about has been labeled. Okay. So the point is that even though this stuff expands the network, a lot of that is uninteresting. I mean, if this were 500,000, this were 1,000,000, you may as well go to sleep before it actually labels something that you care about. Okay? So even though we've thought of this as physically introducing more nodes, but actually you don't need to. That's what this little exercise says. Okay? That you can pretend that you're still doing breadth first search, except that you want to implement it carefully. Restating what I just said, you want to sort of think of these intermediate nodes as being there, but you don't want to draw them actually. So if you just imagine that they are there and think about how the labeling mechanism would proceed, okay, then you have an algorithm that only works with the original network. Okay? So if this were length 6 and this were length 4, I don't have to draw these to figure out that this node would get labeled first, and its label will be 4. Okay? Is that clear to people? So even suppose I didn't have these green nodes, and this arc had a length of 6, and this arc had a length of 4. then I can, in my mind, simulate what would happen if I did have these intermediate nodes and I implemented my breadth-first search algorithm. Okay. What would happen is that at the fourth step, this node is going to get labeled, and this node would not still be labeled. Okay. So this would be labeled first with a label of 4. Okay. So now let's pretend that we introduce these intermediate nodes everywhere and think about the sequence in which the nodes would get labeled. Okay. So obviously this is going to get labeled first. Okay. Then what will happen? So this node has a label of 4, this has a label of 4. In the next step, what would you do? You would explore all the nodes with label 4 and label their neighbors. Okay. So this is going to get labeled as 5, and this is going to get labeled as 5. Okay. There's yet another node that's labeled. Then you're going to explore all nodes with label 5 and label their neighbors. Okay. Here's a label of 5. But remember that there is some green node here with a label of 5 also. Okay. So now you have 3 nodes. There's one green node here with a label of 5. This has a label of 5, and this has a label of 5. Okay. Which node is going to get labeled next? Or which nodes will get labeled next? This is going to get labeled as 6. What else is going to get labeled as 6? This is going to get labeled as 6. Okay. And that's it, right? Any questions about this?
Why not the green node on 5 to 6?
Why not the green node from 5 to 6? Yes. So I draw these. There are 2 nodes. This is going to get labeled as 6 also. Okay. Then, one more step, you're going to label, take all the nodes with label 6 and label their neighbors as 7. Okay. So this node is 6, its neighbor is now going to be labeled 7. Okay. This node is 6, so its neighbor is going to be labeled 7. So and then this is going to be labeled 7. Okay? Is everyone happy with this? And then you would run it one more step when this gets a label of 8. And now, of course, if you implemented the green network or the network with all the green nodes, you are still going to label other nodes that are here, but that's sort of uninteresting because you don't care about them anyway. And once you get to the end, you're not going to use that to label this. Okay? So if you, I didn't do such a great job of explaining how this works, in terms of the full green network, but hopefully I've convinced you that you can actually implement your idea on this network with green nodes without actually looking at the green nodes. Okay? And that's going to lead to our first algorithm for shortest paths, which is the following. At any point in time, I'm going to have certain nodes that are labeled, okay, and certain nodes that are not yet labeled. Using all the labeled nodes, I'm going to figure out the first node outside of the set that will get labeled, and I'm going to add this. Okay. So let me do that directly on this network. So if you had 1, 3, 2, 5, 4, and 6, this has 1, this was 3, 7, so then what will happen is that I'll have this with a label of 0. Okay. Then this is going to be the set of nodes that are labeled. There's only one node, and everything else outside is unlabeled. Okay. Now you're going to figure out the first node outside of this set that's going to get labeled using nodes from this set. So from here, this is going to get a label of 4, and this is going to get a label of 6. Okay. Assuming that, so this is going to get labeled first. Okay. So this is going to get a label of 4. And now from this set, now you look at the closest. Okay. So using this set, this is going to get a label of 6. Okay. This will get a label of 5, and this will get a label of 6. Okay. So 5 is the smallest label that you will encounter, so you label this 5. So notice that you're not allowed to label any other node. Okay. Even though this tentatively gets a label of 6, you're not allowed to label it yet. You're allowed to label it only if it is the closest node that's unlabeled. Okay. So before we did this, there were potentially 3 nodes that we could label using these. So this one would get a label of 6, this one would get a label of 6, and this would get a label of 5. Since 5 is the closest, you label that on only. Okay. And you would continue. So now from here, this would get a label of 6, this would get a label of 6, so you just arbitrarily pick one, or you can pick both. It doesn't matter. Okay. So this would get a label of 6, and this would get a label of 6 also. And now from here, this would get a label of 8, and that's the only label that you care about. So what in effect we are doing is we're just simulating this big network without actually implementing this big network. Okay. So the idea, once again, is at any point in time you have a bunch of nodes that are labeled and a bunch of nodes that are not yet labeled. Okay. Using the labeled nodes, you would be able to label some of the unlabeled nodes. Okay. So compute all of the nodes that are unlabeled now that are reachable from the set of labeled nodes in one step. Okay. And the minimum label that you would assign, you will fix it, and then you will continue. That node will be added to the set of labeled nodes, and you proceed. Okay, so this is the algorithm. Any questions about this? Yes?
So for this type of algorithm, like if you have a one node that's really big, and like say the shortest path only from 1 to to 6, 1, 2, 4, 6, and the 1, 2, 2 say maybe it's really big, but 2, 2, 4, 4 to 6 is really small. So actually these give you the shortest path, but we will eliminate. We will never even go to 2 because like 3 probably is the shortest one to go.
Mm-hmm.
Like I was just wondering, how this algorithm can deal with.
But your algorithm would discover it. So for instance, suppose I modify this network, and let's say that this is an arc actually going this way, with distance 1. Okay. Then what would happen? Well, in the first step, this would be the only label node, and so you would assign a label of 4 to this. In the next step, you would assign a label of 5 to this, right? Because that would, just as this is labeled 5, you could label this 5 as well. So even though this distance is 6, you have a shorter path from 1 to 2, an indirect path of length 5, you would label it, okay, with the right distance. So the key, once again, is that you can only label the node that's outside of this set S, which is a set of all labeled nodes. Pick the node that's closest to this. So pick the node outside that will get the smallest label, and that will be the permanent label of that node. Okay. Yes?
Question. Once you get all the labels, how do you get the shortest path?
Okay, so very good. So I'm going to get to that in a moment, but any other questions about the method itself? Yes?
Actually, so the same question, say if we don't have any of the intermediate paths, we just have the 2 paths from above and below.
Mm-hmm.
And then if 2 is 6 and 3 is 4, we'll never get to 2. But if 2 to 4 and 4 to 6 are much smaller than 3 to 5, 5 to 6, the below should be the shortest path.
Yes, and it will be, right? Okay, so let's do one more example where you have another network. And you have just this. So let's say this has a distance of 10, this has a distance of 4, this is 5 and 5, and this is 1 and 2. Okay. So how would the labeling algorithm proceed? Well, this would get a label of 0. This would get a label of 4. Okay. The next step, look at all the nodes that could potentially be labeled. This would get a label of 10, but this would get a label of 9. So this would be labeled with 9. One more step. If I were to label this because of this, I would get 14. If I were to label this, I would get 10. These are the only 2 nodes that I could label. 10 is shorter, so you would label this. Then, once again, next step you would label this because 11 is smaller than 14. And then now using 11, you would label this as 13. Okay, so you would actually get exactly that. So once again, this is the critical part, that you have to always label that node that it has the smallest label. Okay. Now, to recover the shortest path, what would you do? Just remember who labeled you. Okay. So this node remembers who labeled it. So this node remembers who labeled it. This node remembers who labeled it. This node remembers who labeled it. And this node remembers who labeled it. Okay. So if whenever you assign a label, you just remember your parent, then you can recover the shortest path. Okay. So the shortest path from 1 to 4 is just this, 1 to 5 is just this, but 1 to 6 is actually this path. Yes?
Another question. Is that okay, or is that possible that some nodes don't get any label at the end?
No, every node is going to be labeled at the end.
If, for instance, you hit the definition for a given node.
Well, it depends on the problem that you're solving. If all you want to do is to find the shortest path distance from 1 to this node, and let's say that this, had a label of this distance were 25. Okay, everything else stays the same. This were 25. Then, of course, you would label this before you label that node, and then you don't have to discover all the other labels. But then the problem that I'm solving is find shortest path from node S to every other node, in which case, by definition, I have to label everything. Okay. One last thing, which is what if there is no path from one to the destination? How would you discover that? let's say that you have a network, a complicated network. You want the shortest path length from node 1 to node S to some node T, and T is not reachable from S. So the shortest path distance is infinity because there is no path. But then how would your algorithm discover that? Yes?
Your algorithm would stop because there would be no possible steps at some point?
Yes, very good. So you will stop because at some point you'll have a bunch of nodes that are labeled and there will be no way to get out of it. There will be no way for you to label any other node. Okay. Because notice that you can only label nodes that are reachable. Okay. Any questions about this method? What are the problems that it fixes? So we said if it is, we said the idea of putting these intermediate nodes blows up the network size. This does not, right? You just work with numbers directly and imagine, what would get labeled first. So you're not blowing up the size of the network. You're working with the original network. The second problem that it fixes is that it can deal with fractional lengths. It doesn't care, right? You just look at the minimum label given. If that's non-integer, that's fine. Okay? This is sort of what you said, that if this were 3.5, well, this would get a label of 3.5 and it'd be labeled first. That's the only change. Okay? So it can work with irrational data as well. So there's no restriction on data except that you're implicitly assuming that all the arc lengths are non-negative. Okay. Does anyone see where we're making that assumption? Yes.
We make that assumption because we know that as the case step, we label everything by case, and because we can't label by k after we have labeled by k plus 1, it can happen from negative.
Very good. So yeah, very, very, very good. So the point is that you are implicitly assuming that all the distances grow as you move along. Okay. This is the reason why the minimum label of at any step you have a bunch of labeled nodes, you have a bunch of unlabeled nodes, and if you look at the minimum label that the unlabeled nodes can achieve, that has to be the property we're making use of is that the minimum label has to be the shortest path length to that node. Okay? That can only be true if the labels cannot decrease as you go along. So for instance, it's fairly easy to come up with examples where that would have to fail. So for instance, let's say, let me get rid of this and show you an example where this algorithm would fail if you have negative lengths. So here is 1, here is 2, here is 3, and okay. Now, let's say that this has a distance of 10, this has a distance of 15, and this has a distance of minus 8. Okay. How would the method work? You would, of course, go with this. Then the nodes that are reachable in one step, you would label this as 10, right? That's the first step. Because using this, you can label this as 15 and this as 10. So this is the smallest. So this is what you would label. And then in the next step, well, using this, I can't label anything because there's no way to get out of 2. And using this, I label this as 15. And that's what the algorithm would end up with. Okay? But notice that there is a path of length 7 from 1 to 2. So so this says that the shortest path from 1 to 2 is this one, and the shortest path from 1 to 3 is this one. This has length 10 and length 15. But in reality, the shortest path distances are okay. So this is the right answer, and this is what the algorithm would give you. And notice that, so therefore the crucial property that we are relying on is that when we label a node, that is the shortest path length of that node. Okay? This is the idea, that whenever a node is labeled, you found the shortest path length to that node. Okay? That's obviously not true if you allow negative lengths. Okay? Yes?
I'm not sure whether it's relevant, but this reminds me a little bit about zero syntax. Well, and with that.
No, unfortunately, nothing that I can think of. Yeah, you can of course solve this problem using the simplex method, and we'll get to that in a little bit. Any questions about? So your textbook does not have a proof of correctness of this method. The algorithm, by the way, is called Dijkstra's method. And you have to realize that this algorithm is just glorified breadth first search. I mean, that's the right way to think about it. You're just doing breadth first search on this red graph with these green intermediate nodes, and then you get this algorithm. Okay. There are very efficient implementations. Even the naive implementation runs in time that's quadratic in the number of edges. In the worst case, it's actually quadratic in the number of nodes. So anyway, this is clearly a very efficient method, because at every step you have a bunch of labeled nodes, and then you figure out the node that's unlabeled that would get the minimum label, and then you add it to this set. And this is not such an expensive operation. Okay. So the advantage is it works for any instance of the problem as long as the distances are non-negative. And if you have negative distances, the method could fail. Yes?
Why is this method better than the one we saw last time by backward induction, when we saw it by the last instead of the first?
When we start?
The method we saw last time to deduce the shortest path.
We didn't see any method, right?
What he's saying, like the shortest path from 1 to 6, it's from the shortest path from 1 to 4.
Oh, okay. It's okay. So I see what you're saying. So the question is, why is this any better than exploiting the property that shortest paths have shortest subpaths? So somehow inductively you can build the shortest path tree. That's exactly what we're doing here as well. You're just not making it explicit, but really what you're saying is, if all the distances are non-negative in this case, then you're just constructing shortest paths by looking at, you're still inductively constructing shortest paths. It's a different induction than what you're talking about, and it's not any better. It is better in terms of efficiency. This is a faster algorithm than what you have in mind, but what you have in mind, when made precise, can be made to work for instances with negative weights, negative distances. Okay. And we'll look at that method when we do dynamic programming. As I said, basically that idea is what dynamic programming is, and when we explore that, we'll study a different algorithm for shortest paths. Now, of course, one has to be careful when allowing negative lengths. Okay, I could, for instance, make this let's say I have this. Okay, this has length 10, this has length minus 100, and this has length 15. Okay. What's the shortest path length from 1 to 2. Okay. Well, we attempted to say 10, but actually you could go around the cycle and make it small, okay, smaller than 10. If you do that many, many times, you can drive the cost to negative infinity. Okay? So even if you have negative length arcs, if you have what's called a negative cycle, a cycle such that the net distance is negative, then by going around the cycle many, many times, you can actually drive the cost to negative infinity. Okay? Now, of course, this is not what we mean by a path. What we mean by a path is a way of getting from some node to some other node without traversing any cycle. Okay? So if that is your definition of a path, in the presence of negative cost cycles, it's not easy to find the shortest path distances. That's a very difficult problem. Okay? If you don't have negative cycles, then shortest paths are well defined because there's no reason for you to traverse the cycle, because every cycle is going to have non-negative length. Okay? In that case, shortest path distances are well defined, and we will discuss an algorithm to compute shortest path distances, but that'll have to wait for a little while. Okay? So for now, we know a method to compute shortest paths when the arc lengths are non-negative, and take it from me that there is a method that would work when arc lengths are negative as long as there are no negative cost cycles. If there's a negative cost cycle, then shortest paths are either undefined, or if you define it the way I defined it, there's no revisiting nodes, then computing shortest path distances is what's called NP-complete. It's actually much, much more difficult. Okay? So that's going to be the end of the short discussion on shortest paths. In your homework, I'm going to ask you to prove the correctness of this method with a lot of hints. Okay? It's not in your textbook, but it's instructive for you to understand how such a proof might work. Okay, so that's about this. Now I want to discuss the maximum flow problem, except that there's only 5 minutes, so it doesn't seem like a useful thing to do right now. So we'll meet Tuesday. We'll start with max flows and then quickly do minimum cost flows. And by Tuesday, certainly by Thursday, we'll wrap up network flows. Okay. Oh, one last thing. If you're interested in network flows in general, this is sort of an appealing topic in terms of practical applications and so on. So this is a book called Network Flows by Ahuja, Magnanti, and Orland. It's about 10, 12 years old now, but it has a very good discussion of applications, methods for solving these problems, complexity issues. So it's a very, very nice book on this topic. Of course, this can be used at many levels, including at the PhD level, where there's a course on network flows that's sort of based on this book. But I just thought I'll mention that if at all you find this topic interesting and you want to study more, this is the place you want to go look at.